And yeah, you guys can, even though it's recording, you can ask questions, interrupt if you need to. No problem. Okay, so go ahead and just title this first page atoms. All right. And we're going to draw an atom. Okay. So remember that all atoms have a nucleus. So we're going to start with the nucleus. What is this positively charged particle in the nucleus called? Proton. Okay. And then what are these neutrally charged particles that are in the nucleus called? Neutrons. Okay. Very good. And so far, okay, just based on the count here, we've got 2 protons. So just look up there at that periodic table. Can you guys tell me what atom this is? Helium. So for those of you who are novices to the periodic table, if you look in each of those squares, there's a number at the top right-hand corner written in blue. It's the biggest number on there. And if you look up there at the top right, helium, He, has a blue number 2 at the top, and that tells you the atomic number, which is how many protons does it have. Okay. Then we got 2 electrons that are orbiting this nucleus. Also, the electrons are each negatively charged, -1. And if you want, just say, okay, this is a helium atom. So just to kind of recap, we got for the subatomic particles, a proton has a mass of approximately 1, a charge of +1. A neutron, remember, is also a mass of 1. I haven't said that yet, but just know that those neutrons, even though they're neutral, they still have a mass of 1. They're just as heavy as a proton. However, as we said before, their charge is 0. And then electrons, right? Mass of about 0. Now I put about because they do have a mass. It's just so small that it's pretty much negligible. And then a charge, of course, is -1 for the electrons. Okay. All right. Now, if you ever see like a reaction written out, okay, you'll often see a notation that's used. You'll see the letters that represent the element, and then you'll have a number up here, and then you'll have a number down here. And what you need to know is that this top number represents what we call the mass number, MASS number. And then this down here represents the atomic number. So let's just go ahead and decipher that real quick. What is the mass number? Notice that the mass number is larger than the atomic number, right? It's the bigger number. So the way that you figure it out is you have to take the sum of the number of protons and neutrons. Because remember, you guys, those are the only 2 particles that have a mass. The electrons do, but it's so small that we kind of ignore it. So if you want to know the mass number, you got to count up all of these in the middle. 1, 2, 3, 4. Okay, so this must have a mass number of 4. For the atomic number, the way that you figure that out is you just count the number of protons. So if I just look inside the nucleus there, 1, 2, atomic number is 2. And remember, the atomic number is kind of the ID, the identification, especially when you're looking up there at the periodic table, that big blue number. Now, I know that this is already confusing because you're like, wait a minute, I thought the atomic number was at the bottom of the element. And up here, the atomic numbers, they put it up at the top right, and then the mass numbers down here. I'm sorry, I wouldn't have done it that way, but that's how they do it in chemistry. So just when you're looking at the periodic table, just you have to flip those numbers, I guess. Okay, isotopes. Anybody know what an isotope is? Can anyone tell me? You chemistry experts? Yep. Excellent. It is a version, you could say, of an atom that has extra or fewer number of neutrons. All right, so this is what's key with this, you guys. If you change the number of neutrons, do you change the ID? Do you change the identification of the atom by changing the neutrons? No, you don't. Because remember, you guys, that the identification is determined by the proton number. So we can add neutrons, take away neutrons, and that doesn't change the proton number. So it's still going to be a carbon atom. So the example we're going to look at here, just for the isotope, is well, and I'll add that the element ID stays the same because the proton number is the same. Proton number is unchanged. So, for example, you could have carbon 14 is an example of an isotope out there. And, most carbon atoms are just the regular carbon 12. But, even in this piece of wood right here, there's some of the carbon atoms that are in here. Some of them are isotopes. Some of them are carbon 14. A percentage of them, a smaller percentage. So this isotope here, this carbon 14, there's a couple things I want to say about it. It has 8 neutrons. Normally, carbon has 6. So we know right away that this is an isotope because it's got those extra neutrons. And if we wanted to figure out the mass, you would do the 8 neutrons plus the 6 protons equals the 14 units of mass. So there's where we got the 14, right? It's carbon 14. That's the mass. That must mean that we've got the 6 protons, because remember, identification of carbon is the number of protons. That's what makes it carbon. So it's got 6 protons. You got the 6 protons plus the 8 neutrons adds up to 14. All right, now what about the regular elemental carbon? Regular carbon 12. We'll just say that that's elemental carbon. And that this has 6 neutrons. And so therefore you got your 6 neutrons, your 6 protons, and that adds up to 12. Any questions so far about that? All right. Pretty simple. And then let me remove that waste basket. I'm not supposed to pop my load. Okay, so in nature, carbon 14 is unstable, and it is prone to decay, but it's only slightly unstable, which means that it actually takes a while for it to decay. But this might confuse you a little bit. You might think that it decays it back to carbon 12, but it doesn't. It actually, what carbon 14 will do is it'll actually decay into something called nitrogen 14. Okay. Don't worry too much about that, but just know that carbon 14, that just know that isotopes are generally less stable than the regular version. And so this carbon 14 is going to decay. It's going to want to shift, right, into something else. And what I want to say is that carbon 14, it decays at a very predictable, steady rate. A steady, predictable rate. In fact, it takes 5,730 years for 50% of the carbon 14 to decay. So for half of those carbon 14s to decay, it would take 5,730 years. Anybody know what that's called? This half thing? Yeah. Half-life. Yeah, it's the time it takes for half of it to decay. So just like, mathematically, what that would look like on a graph, say that you had like eight eight carbon 14 atoms, and then you have 4, 2, 1. Anyway, and you kind of like plotted this out, you would get, this is time. So like, let's say that this is 5,730 years. And then this little tick mark represents twice that amount of time. And then this little tick mark represents 3 times that amount of time, or 3 half-lives. What you can expect is in that first 5,730 years, it's going to decrease by half. So what's half of, if you're starting with 8, what's half of 8? 4. If another 5,730 years passes, we will cut it in half again. And when 4 gets cut in half, that leaves us with 2 atoms left. If another 5,000 years passes, it gets cut in half again, and now we're down to 1. And then if 1 gets cut in half, so on and so forth. But it kind of does this asymptote sort of at, right? It never really reaches 0. Anyway, you can add that in there. Okay, so why do we care about that? Well, it turns out that if you know the percent of C14 remaining, you can calculate how long it's been decaying for, right? How many years it's been decaying, which is its age. So this is what we call carbon dating, okay? Carbon date a fossil. What you're doing is you're just analyzing how much carbon 14 is still there. And if there's hardly any, that means it's been decaying for a very long time, right? So, questions about that? Cool. Yeah. So the carbon dating, that's just a part of this isotope thing. Okay, so let's start the topic of valence electrons now. Valence electrons. Okay, so a couple fun facts about valence electrons. valence electrons are the electrons in the outermost shell, which is also known as the valence shell. Okay, so that's your definition. And then something to note is that if the valence shell is full, the atom is stable and unreactive. So there's a connection between stability and reactivity. In fact, the more stable something is, the less reactive it is. So, example, the noble gases. Okay, so over here, this column of elements right here, all these red ones, those are called the noble gases. Helium, neon, argon. And one of the things that characterizes them is that they're just really stable. They don't react with anything, really. Very unreactive. And the reason that they are is because they're on the end, the far right-hand column. That means that they have a full valence shell of electrons. They've got all 8 electrons in their valence shell. So what would that look like? Let's just take neon, for example. Neon has a nucleus, and when you do these drawings, you don't have to draw all the particles in the nucleus. The fastest way is to just be like, okay, neon nucleus, and then circle it. And so neon has 2 shells, and inside the most inner shell, there are 2 electrons. And I know that might be a little confusing, but the innermost shell always has 2, and then the next shell has a capacity for 8 electrons. So out here, we've got 1, 2, 3, 4, 5, 6, 7, and 8. And so what we want to say is that this outer shell is complete with 8 electrons. That's the capacity, right? So to have all 8 means that you are full to capacity, and therefore very stable, very unreactive. All right, so that's good. So that's neon, But let's contrast it now. Let's contrast that with something that's unstable. So if the valence shell is not full, then the atom is unstable and very reactive. So the perfect counter example here would be sodium. Sodium is like neon, but it's like 1 electron more. So, and the reason we know this is I think I need my laser pointer. So. Anyway, just look at how the position of I was trying to make my face. Look at the position of neon, and then look how if you went, which by the way, you guys, this is like the periodic table is like reading, like you read from left to right, and then once you get to the end, you go back to the next line. So it goes like this, and then you jump to here, and then when you get to here, neon, jump down to here. And then also just notice the numbering. Neon is 10, sodium's 11. Okay, so why is this significant, and how does this relate to the valence idea? Well, if you add up the electrons and you see where they fall, you find that sodium will have this one, right? The second shell will be just like neon. In other words, it fills it up. But notice that sodium, according to the periodic table, so once again, we look at that number right up there, 11. Neon is 10. That number means that we have 11 electrons. So right now, how many have we accounted for? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Shoot, we got one more. Where's that bonus electron going to go? Well, it can't go in this orbital is occupied. It's already full to capacity. So now we got to have this extra orbital with a loner electron out there. So loner valence electron, unstable, highly reactive. It's not happy, right? Neon was really happy. It's like satisfying to have everything filled up and stable. So I don't know if you guys have ever seen. Did Miss Calmer ever put like any potassium in water and show you how it like bursts into flames and stuff? You ever do that? Yeah, so that's why all these alkali metals, they all are just like sodium. They all have this loner electron. And so if you just threw like a chunk of potassium into water, it like sparks and like goes crazy. And that's because it's reacting with the water with this lone electron. And also, the further you go down this way, the more reactive they get because those valence electrons are now even further out, which makes them even more unstable. And so it like potassium's pretty reactive, or sodium's pretty reactive. Potassium's even more reactive. And then I believe that francium, this one at the very bottom, is so reactive that you can't even have it like it can't even really exist because it just reacts immediately with everything. Like, so it's kind of some of these elements are just like really unstable, so they only exist in very particular conditions. All right, so now electronegativity. Electronegativity. The definition is a tendency of an atom to attract electrons to itself. And there's different electronegativities. And generally speaking, the trend on the periodic table is kind of like, I think it's kind of like this. So generally, so you got like high electronegativity. Then you got low electronegativity. So just generally, and I think there's exceptions, but the general trend is that if the atom that you're considering is kind of more toward the top right, it's probably going to be more electronegative than something that's on the left-hand side. And the reason we care about electronegativity is because it results in unequal sharing of electrons in molecules. So say that you've got a water molecule and you got oxygen binding to hydrogen. Well, hydrogen and oxygen, they don't have the same electronegativity, so there's an imbalance, and we'll show you that in just a second. But it results in unequal sharing of electrons, which makes the molecule polar? Underline polar because that's a key word that we're going to have to know. So let's look at what this would look like in a molecule. So you guys know, right? Atoms are the individual pieces, and then molecules are what you get if you connect multiple atoms. So let's just look at our most cherished molecule for biology, water. So water is H2O, and so we have this oxygen atom. And how many electrons does oxygen have? Why don't you guys look up there? Somebody shout out the number of electrons that oxygen has. 8. That's right. Yeah. The proton number is also the same number of electrons. You have the same number of protons as you do electrons. So whatever the blue number is, that's the number of protons and electrons. So we got 8 electrons, 8 protons. So let's see where these 8 electrons will fall on the outermost shell. So the inner shell will have 1 and 2. The outer shell will have 3, 4, 5, 6, 7, and 8. And they're going to go like that. They're going to be kind of, you can think of oxygen as having 2 unpaired electrons out there. Now, hydrogen is atomic number 1, which means it's got 1 electron. So if we draw a hydrogen atom, that would look like this. Okay, so look at this. This is perfect. This oxygen is missing. This oxygen atom would love to have 2 more electrons. Because, right, the stable form would be where it's got 2, 4, 6, 8, right? So it just needs 1 more here, and it needs 1 more here. And so the perfect solution is to react with 2 hydrogen atoms, form a covalent bond, and then you've got a really stable molecule. So what would the water molecule look like if that takes place? Then it would look like this. There you go. So there's a water molecule. However, well, actually, before I say that, I want to point something out here. Right in here, this bond that connects the hydrogen to the oxygen is called a covalent bond. All right, now let's break down the word covalent. You guys ever do that? Break down the word into its roots to kind of try to decipher it? So what does co mean? What's a co-worker? Someone you work with. So co just means with. And then valent, well, we already know what valent means. Valent is the outermost electron. So what this means is that it's a covalent bond is when valence electrons are being shared with each other, right? The atoms are sharing them with each other. So we've got a sharing of valence electrons between an oxygen and a hydrogen atom. Another thing to note about the covalent bond is that it's very strong. It's a very strong bond, which means water is going to stay together. It's going to be unlikely that water will separate. Okay, but now the electronegativity thing. I told you guys that atoms have different electronegativities, and that generally when you move from left to right, you become more electronegative. So between the 2 atoms, take a look up here. We got water is this and this. Which of those two atoms is going to be more electronegative? More electronegative? Oxygen, right? So let's say that. We're going to say oxygen is more electronegative than hydrogen. So, therefore, another thing I want to point out, you guys, is when we do these drawings, we show the electrons all nice and huddled up and nice and evenly spaced and just kind of sitting like that. That's not realistic at all. Like, we do that for convention just to make it easier. But the reality is that it's more like a cloud of electrons. So just picture like a blurry cloud that represents where those electrons could be, and they're zipping around faster than you can even imagine, right? But you got kind of just a cloud instead. So I'm going to say the cloud of electrons is closer to the oxygen side of the molecule because oxygen is more electronegative, right? This makes, by the way, like, let's just point out the obvious, but electrons are negatively charged, right? So the oxygen side will be more negative than the hydrogen side. Okay, triple star this, because that's like, I don't know. There's some stuff that just never fails to be on the AP tests, like, and this is one of the things that just is always on there. So anyway, triple star it. Make sure you understand that idea. And so now that we know that, go ahead and take your pen and make this side of the molecule be really negative and make this side be positive. Because we know that the electrons are all kind of hovering more around the oxygen. Any questions about that? All right, we're done with the notes. So hopefully this helps you guys today with your P table. But I'd like you guys to go ahead and